So if we calculate, although we have not calculated how many people read exactly A, how many read exactly B or exactly C, but together they are 30 in number, and 52 people read at least one newspaper. Now we can also answer something which has not been asked in this question. How many of those 60 people do not read any of the three newspapers? Which is now easy. It is 60 minus 52. 8. 8 people don't read anything. Don't read any one of these three newspapers. Okay, so this is how we can answer some of this type of questions. Okay, where a number of certain people is given. Who I have chosen the more complicated one involving three sets because it shows you all the different possibilities of finding how many number of people read newspaper A, and okay, we can also try to find how many number of how many people read exactly newspaper A. So that is left to you. Okay, you have to find this thing. Think about it. Number of people reading newspaper A but neither B nor C. The cardinality of this set. You try to think of this. And now we go to the next question. I hope the answers I found are numerically correct. You please re-verify the calculations. Sometimes you can understand what you have done is correct or not. For example, that there where I tried to find the cardinality of this set that I have asked to find you now, asked you to find. So there I was getting negative result. Okay, so that is an indication that I have made a mistake. But more often, we will not know what the mistake is if we have committed some error. So let us now go to the second question. Show that this is again a theoretical type of question, but that question, that type where you are given a number of people or something else of this type, that type, so that is one type of question which is just like this. Either you have two sets involved or you have three sets. It's rarely a case that four sets are, I personally have not come across any such problem where four sets are involved. But you know from the general formulation of this formula where we try to find the number of elements in a union of a number of sets. Okay, I have already told you how to write the formula down. First you add the cardinalities of the individual sets, then minus the cardinalities of the intersections taken 2 at a time, then plus cardinalities of intersections taken 3 at a time, and it goes like that. So if you come across a problem that involves 4 or more sets, although it will be huge and somewhat cumbersome to calculate, but it can be calculated nevertheless using the extended formulas. So now we come back to a theoretical problem. Show that for sets A, B, C, A intersection B equal to A intersection C does not imply B is equal to C. Okay, so this we have to show. Show that PA is equal to PB implies A is equal to B. Okay, this also we have to show. Also, there is one more part. Show that A cross C is equal to B cross C implies A is equal to B if C is non-empty. Okay, so we solve them one by one. Solution. First, we try to show that A intersection B is equal to A intersection C does not imply that B is equal to C. It's not always the case that whenever these two intersections are equal, we must have B is equal to C. That's not always the case. So, to prove something like this, to prove something does not happen, if you recall what we have discussed in the videos on mathematical logic, to prove that something does not happen, you just need to produce one example where it does not happen, and that example is called a counter example. Okay, so here also we have to find a counter example. That means we have to find some sets A, B and C for which this is true but this is not true. Okay, and it's not very difficult if you think about it. For two intersections to be equal, but the steps are not equal. For A equal to, okay, let me choose A later. First I choose B. So I take B equal to 1, 2, C equal to 1, 3, and A equal to 1, 4, 5. For these three sets, we have A intersection B is what? There is only one element common, which is 1, so 1, which is also equal to A intersection C. You see, here also only one element is common, which is number 1. But clearly B is not equal to C, because they are not equal, you can see. B has 2 which is not there in C, C has 3 which is not there in B. So this answers the first part of the question. For the second one, what do we have to show? We are given that for two sets A and B, their power sets are given to be equal. We have to prove that A is equal to B. Okay. So A is equal to B means you already know how to show two sets are equal. You have to show that each one is a subset of the other. So let A be any element of A. We have to prove that this element belongs to B also. So what is given to us is this. So somehow we must be able to use this one. But it's a statement about power sets. That means subsets of A. Now, but you are given an element of A. So using this element, we can form a subset. The subset consisting of this element alone, singleton subset. Then this subset, this is an element in the power set of A. Look at this carefully. It is an element in the power set of A, not a subset of power set of A. It's a subset of A, not of P of A. It's an element of P of A. Since PA is equal to PB, we have this belongs to PB. But for a set like this to be in PB, it simply means that this is a subset of PB. This is a subset of B. Okay, this implies, because PB is precisely the set of all subsets of B. So this being in PB means it's a subset of B. This implies this is a subset of B. So that means every element here must be in B. So this has only one element A, so it must be in B. And so A belongs to B. So having chosen an element in A, we have proved that that element is in B. Hence, A is a subset of B. Similarly, we can prove that B is a subset of A. Hence, A is equal to B. So the second part is also over. Finally, we look at the third part. Okay, these are separate problems, but I have chosen to state them together. Okay, so we have to show this. Now here I want to draw your attention to something else. You see, sometimes sets behave like numbers. If instead of these sets we had numbers like this, A and C, and instead of Cartesian product we had ordinary multiplication, BC, you then have a rule which tells you that you can cancel out C from both sides, provided if C is not equal to 0. Now, if we think of the empty set as corresponding to the number 0, then this one looks just like this. So it's a sort of cancellation formula. Although instead of numbers we have sets, and we have operations between sets. Here we have operation between numbers. Ordinary multiplication, this is Cartesian product. Okay, this condition is necessary. Without this condition, we cannot make cancellation here also. Okay, so to show this, again we have to show A is equal to B. So let A belong to A. Since C is non-empty, there exists some element we have been able to choose this element only because C is non-empty. Being non-empty means having some element. So we have chosen any element. Then where will this ordered pair be? The first coordinate is in A, the second coordinate is in C, so that means it belongs to A cross C. But we are given that A cross C is equal to B cross C. Since A cross C is equal to B cross, I don't really know whether I should call it cross. It's better to say Cartesian product. A Cartesian product C equal to B Cartesian product C. We have A comma C belonging to this set. This implies Now an ordered pair belonging to a Cartesian product means what? The first coordinate must belong to the first set, the second coordinate must belong to the second set. So this implies A belongs to B and C belongs to C. Now C belongs to C, we already know that, but this is new information. We have shown that A belongs to B, having chosen that A is an element of A. Hence, A is a subset of B, and the rest is same. Similarly, you can show that B is a subset of A, and so A is equal to B. So this completes the solution to this problem. Now the next one, apart from this somewhat more difficult problems, there are some very simple problems in set theory. For example, a set will be given to you, and in for instance, the rule method or set builder method, you will be asked to write it in roster method or vice versa, things like that. You may be asked to ascertain something like this, whether this is true or not. Is it true? This is not true. This set has three. In one example, I have already discussed something like this, right? So where a set has elements, some of which are sets. This set has three elements. This is one element, this is one element, this is the other element, and one is none of them. So one, although it is in this set, but it does not belong to this set as an element. So this does not belong to this set. Or if it is given like this, then this statement is false. So things like that may be asked. But here we are solving somewhat the more complicated problems, relatively more complicated. So the next one is again a theoretical problem. It asks, okay, show that for sets A and B, PA intersection PB is equal to PA intersection B. Okay. Also, A union B equal to A intersection B implies A is equal to B. So this problem has two parts. The first part asks us to show that show this identity. Okay, so this is usual thing. We have to prove that two sets are equal. So we have to show that each one is a subset of the other. So we start the solution. Right. So first of all, we can we do this? Let me think. A intersection B is a subset of A. So okay, yes. Since A intersection B is a subset of A, look at this carefully. Any subset of A intersection B is also a subset of A. Why? Because this is A, this is A intersection B. I am not showing the full B here. A intersection B. So here if I take a subset, any subset of A intersection B will look like this. So it is automatically inside A because it's inside A intersection B, which is inside A. Okay, so that means any subset of A intersection B is an element in the power set of this set, and any subset of A is here. Hence, PA intersection B is a subset of PA. We have obtained this. Similarly, PA intersection B is a subset of PB, because B is also a A intersection B is also a subset of B. So from that we will get this. Hence, if you have two sets, okay, and one set is a subset of this one also and that one also, then it is a subset of their intersection. It will belong to both of them. So here also the same thing. PA intersection B is a set which is contained in both PA and PB. So it will be contained in their intersection. So this is contained in or a subset of the intersection. So we have been able to show one part of this equality. One part means in the sense that this one, this relation. Now we have to show the opposite one. We have achieved this one without considering any element. Okay, but for the opposite one we have to consider element. Next, let. But here element means what? These are power sets, an intersection of two power sets. Inside a power set you have subsets as elements. So when we consider an element here, that has to be a set. Let C be an element, mind it, of PA intersection PB. Then C belongs to PA and C belongs to PB, or in other words, C belongs to PA means what? C is a subset of A and C belongs to PB means C is a subset of B. This implies C is a subset of A intersection B, or we can write it like this. Or C belongs to P A intersection B. Being a subset of A intersection B means being an element in the power set of A intersection B. So having chosen C here, we have shown that C is here. Thus, this intersection is also contained in this power set. From these two relations, this one and this one, you have equality. This is what you have to show. So this is the first part of the solution. For the second part, we are given this. A union B is equal to A intersection B. We have to show that A and B are equal. We can do this by considering elements and in the usual way showing that A is equal to B. But instead, I would like to try the set-theoretic relationships or identities here so that we can get the job done without considering elements. Let me see if that is possible. From A is contained in A union B, we have, you recall that this is one of the properties of unions that we proved when we introduced the operation union. So because this is a subset of A union B and A union B is given to be equal to A intersection B, we have A is a subset of A intersection B. But we also know, now corresponding to this property, for intersections we have this. A intersection B is a subset of A. Hence, so this is a subset of this is a subset of this is a subset of this. So they are equal. A is equal to A intersection B. Okay. But this also we know, if you remember, the last property of intersection says that if the intersection of two sets is one of them, then that is a subset of the other set. But this implies A is a subset of B. Okay. Similarly, we cannot write similarly here because a lot of argument is involved. Okay, we have to carry out the corresponding argument for to get the other containment. So again we start from, okay, what should we do? Let me take B. B is a subset of A union B. B is also a subset of A union B. We have, it will now go similarly. We have B is a subset of A intersection B. From, since we know this one also, that A intersection B is a subset of B, we thus get B is equal to A intersection B. Okay, we need not have written this one. We don't need the last property of intersection, because you see, if we come to this part, I mean, if we have got this identity, I mean this equation, and we have got this equation, then from them we automatically have A is equal to B. That's what we wanted to show. So sometimes it's beneficial to not go all the way. Okay, you can stop somewhere and then use, and you can see that we did not have to go down one level and work with elements. We have been able to work with sets as if they are numbers. Okay, this somewhat looks like A is less than or equal to A plus B. Things like that. Okay, some analogy is there. Sometimes, if we know enough set theoretic identities, we can work with just sets. So this ends this solution. There is one more problem. Let A be the set of those triangles in the plane. Let A be the set of those triangles in the plane, that A with a set of those triangles in the plane that have at least one angle not equal to 60 degrees. Describe a complement. Okay. There is one more part, although completely unrelated, but this is the only remaining problem. So let us see both of them together. Show that the set is not the Cartesian product of two subsets of R. The second one looks more complicated than the first one. It is, but we will see that this is actually something we have encountered. Okay, so let us deal with the first one first. Let A be the set of those triangles in the plane that have at least one angle not equal to 60 degrees. Describe a complement. So we are talking about the set of triangles in the plane, different types of triangles. So in this context, the universal set is the set of all triangles in the plane. Okay, they may contain triangles of any shape, any size. Now among them, we have chosen those triangles which have at least one angle not equal to 60 degrees. Okay, so you can have different types of combinations. For example, you can have something like this, where this angle is 30 degree, this angle is 60 degree, and this is of course 90. So that their sum is 180 degree coming from plane geometry, that result. So here at least one angle has to be not equal to 60 degree. Here we have two angles not equal to 60 degree. So this is a triangle in this set. So A is the set of such triangles. Now if something is not in A, then that must be a triangle where all the angles are equal to 60 degree. And you already know from plain Euclidean geometry that such triangles are equilateral triangles. Hence, in this solution, you can just simply write, since a triangle all of whose angles equal 60 degree is an equilateral triangle. A prime is the set of all equilateral triangles in the plane. So A prime is the set of all equilateral triangles in the plane. So that is the first part. Now the second one. What does the second one say? The second one has a set. Okay. Now this set is a subset of R cross R, where R is the set of real numbers. You recall this blackboard bold type of R represents the set of real numbers. This symbol has been reserved for that set only. Okay, so not all ordered pairs of real numbers. If you recall, in one of our discussions, we have already, the one where we introduced Cartesian products, we have seen that we know this R, Cartesian product R, as the plane of a graph paper, where we can draw graphs of equations. If someone draws the graph of this, although it's not, technically speaking, it will not be a graph, but nevertheless, this equation can be drawn, okay, or the points satisfying this equation can be drawn. For example, you already have 4 points which are very easy to determine: 0, 1, 0, -1, 1, 0, and -1, 0. These points satisfy this equation if you take x to be the first coordinate and y to be the second coordinate. 0 square plus 1 square is 1. 0 square plus -1 square is 1. 1 square plus 0 square is 1, and -1 square plus 0 square is also 1. And these points